So folks, we're continuing with our discussion of linear transformations. And one linear transformation that we could look at is the dot product operation. So one way to look at that is if we have a vector space V, then this mapping is going to map from your vector space to the space of real numbers. So for example, if I were to take, let's let V equal the vector 1, 1. Oh, let's do 1, 2, just so it's a little different. 1, 2. And if I were to look at D of V of the vector U, where U is the vector 2, 4, how do I do that dot product? Well, how would I do this linear transformation? I would take 1, 2, and I'm going to dot it with the vector 2, 4. And when I do that dot product, I get 1 times 2 plus 2 times 4, which gives me 2 plus 8, or 10. And so what do we notice? We notice that this transformation took a vector u and mapped it to the number 10 under the transformation of dotting it with the vector v. So we can think of that as a linear transformation. In proving that the above transformations are linear, we're simply using the linear properties that you've already proven about these operations in earlier classes. So it may feel a little bit redundant when we go through proving some of these things are linear operations because you've been assuming they're linear operations or linear transformations for a long time. There's a note there in 7 that I'll let you read through. Let's look at something that isn't a linear transformation. We could talk about, we know that the space of real numbers is a one-dimensional vector space, and we could have an operation that takes us from R back to R by S of some real number is just the square root of that real number. But we see that that's not a linear transformation. Remember, what does it have to be? What do we have to satisfy to be a linear transformation? We need to satisfy these two properties, that you can do the addition and then the transformation, or you can do the transformation and then the addition. And we need to verify that you can do scalar multiplication to the vector and then the linear transformation, or you can do the linear transformation to the vector and then scalar multiplication. And the order in which you do those does not matter. So I want you to think about why this isn't true, give it a shot, and then take a look at the solution there. Now, the big reason for doing all of this is because I want us to now think of nth order differential equations as being themselves linear transformations. So we'll take some function y and then we'll do the left-hand side of a differential equation to that function y. That's a little bit strange to think about it, but the way it would work is this. Let me just convince you, before you do the proof, let me just convince you that what we're talking about is a linear transformation. I could take the function y equals, I don't know, x to the 5th power, and I could do else of y to it. Well, else of y would mean to take 3y double prime minus the sine of x times y. And so what I would do is I would just go ahead and do these operations to my function y, and if I did so, I'd have, this would be 25 times 4, 20, so 3 times 20 x to the 3rd minus the sine of x times x to the 5th, where I replaced the y here with x to the 5th, and I replaced the y double prime here with the second derivative of y. And we got this new function, in this case 60x to the 5th minus 60x to the 3rd minus x to the 5th sine of x. So the way you can think about this is we're taking a function here, a function from the function space, and we're mapping it. I guess it'd have to be, if we're going to take two derivatives, it has to be, usually we'd say from C2. And we're going to map it to the, hopefully it'll be continuous. And we're taking this function y and we're mapping it to the function 60x cubed minus x to the 5th sine x. That's a very abstract way of thinking about taking a function and checking to see whether it solves a differential equation. That's really interesting. Okay? So it turns out that if we treat the I like to think of it as the left-hand side of a differential equation as a linear transformation, or as a transformation, we can show that that transformation is linear. So take a look at the proof of that, and you'll see that the reason why the proof works is because of the linearity of the second derivative operator and the linearity of just the way we've written the left-hand side of a linear differential equation. So take a look, fill in that proof, and I'll join you in the next video as we look at superposition.